T701D engine. The T700 GE701D engine is a front-drive, turboshaft engine of modular construction. The engine is divided into 4 modules: cold section, hot section, power turbine section, and the accessory section. Through upgrades in materials and the design of the T701D, it provides better performance in hot and high altitude conditions than the prior designs. Engine control system. The engine control system consists of a DEC, Digital Electronic Control, or newer enhanced Digital Engine Control Unit, EDECU. Engine quadrant, load demand system, and speed control system. The DEC/EDECU is mounted below the compressor casing and is cooled by airflow through the stroll case. Digital Electronic Control, DEC. DEC controls the electrical function of the engines and transmits operational information to the cockpit. The DEC can be fully powered by either the engine alternator or by 400 Hz, 120 volt alternating current helicopter power. The DEC incorporates a negative 112 degrees Celsius TGT bias at any time that the DEC is powered, either by the alternator or by the aircraft power. Whenever the DEC is not being powered, an unbiased TGT indication will be displayed to the crew. Complete loss of engine alternator will result in loss of NG signal, with corresponding engine out audio and light. Airframe power will sustain the DEC, and there should be no failure of the engine to the high side or loss of torque or NP indications. Accept inputs from other sources for electronic control of the engine. That's the engine alternator, thermocouple harness, NP sensor, torque and NP overspeed sensor, torque signal from the other engine for load shoring for torque 1 and torque 2, collective position transducer for improved transient droop response, which is mounted on the mechanical mixing unit, NR sensor, which is mounted on the left accessory module, the engine speed trim switch for NP1 and NP2 demand speed reference, feedback signal from the hydromechanical unit for response and torque system stabilization. Linear variable differential transformer, LVDT, is also provided. NP overspeed switch signals to the ODV and the A and B button. Provides the following signals to the cockpit. NP, initial indication is at 4,000 RPM, allowing earlier visual display during engine run-ups. Torque signal is locked to 0 until NP reaches 35%. This logic eliminates torque spike signaling during engine start and shutdown. This prevents yaw excursions caused by load sharing response to torque spike during in-flight restarts of an engine. Additional and modified operational features. Hot Start Preventer, HSP, automatically prevents over-temperature during engine starts by shutting down the engine. Requires 400 Hz, 120 volt alternating current power for operations through the APU generator. Requires signals from the NP sensor, NG alternator winding, and thermocouple harness for TGT. HSP activates a solenoid in the ODV, which shuts off fuel flow to the engine when NP and NG are below their hot start reference values, and TGT exceeds its reference value. For NG, it'll be under 60%, NP under 50%, and TGT greater than 900 degrees Celsius. In an emergency, HSP can be disabled by pressing and holding either of the NP overspeed test buttons during the start. To ensure the system is disabled through the full start sequence, hold the button until NG is over 60%. Transient droop improvement. The engines are more responsive to aircraft maneuvers by preventing a collective and NR rate compensation. Signals required. NR sensor is mounted on the left accessory module. Collective position transducer is mounted with the 2 previous transducers on a modified bracket assembly inside the MMU. Engine torque signal. The NR and collective signals are routed to rate circuits in the DEC and EDECU compared with NP and torque signal values. A priority signal is then processed to quickly trim the torque motor in the HMU to compensate for the demand. Transient droop improvement is 4:1 over the T700 GE700 engine. If a sensor fails or a malfunction occurs, then the system reverts back to the basic load demand system similar provided by the ECU on the T700. TGT limiting. The DEC and EDECU commands the HMU limit fuel flow engine when TGT reaches the limiting value. TGT limiting does not prevent over-temperature during compressor stalls, engine starts, or when engine power control lever is in lockout mode. When maximum power is being demanded, transient increases above the limiting values can be expected to occur. TGT limiting results in the following. Dual engine 10-minute limit value at 879 degrees Celsius plus or minus 9 degrees Celsius. The UH60M with DCU, source from the TM, single engine 2.5 minute limiting value, also known as contingency power, at 903 degrees Celsius and negative 10 degrees Celsius plus or minus. Note, automatic contingency power is provided by the DEC. The dual engine 10-minute limiting value will automatically switch to the higher single engine 2.5 minute limiting value when the opposite engine torque is shown as less than 50%. NP overspeed protection system. Primary electrical source is the engine alternator and secondary source is the 400 Hz 120 volt alternating current airframe power. System is tripped when NP reaches 120% plus or minus 1% at 25,000 RPM. When an overspeed is sensed, both overspeed sensing circuits A and B, the overspeed protection relay will activate the overspeed solenoid in the ODV. The ODV shuts off fuel and sends a signal to the delay on dropout unit, DODO, circuit turning on the ignition. When NP drops below 120%, plus or minus 1%, the overspeed solenoid valve automatically closes, allowing fuel flow to return to the engine. When the overspeed solenoid valve closes, resupplying fuel to the engine ignition will come on, channeled through the overspeed relay, and remain on for 5 seconds to allow for restart. NP overspeed protection is still functional during DEC operations and lockout. Enhanced Digital Engine Control Unit, also known as the EDECU or EDECU. The EDECU is a common engine control installed on the UH60M. The functionality of the EDECU is nearly the same as the DEC with a few minor exceptions. Those exceptions are: unlike the DEC, the EDECU is not dependent on the other engine's torque being less than 50% in order to operate. Fuel flow is regulated to hold a constant TGT. It is normal to see a transient increase above the 903 Celsius TGT limit when the pilot demands maximum power. The EDCU has discrete application selection, also known as a DAS plug, installed, allowing the engine to operate with 701 delta limiting values. Upon power-up, the EDCU will send a signal validation to the associated engine torque meter, indicating its configuration. The EDECU will display a signal of 25% torque, plus or minus 3% on the torque gauge for 20 seconds after initial application of AC power and prior to indicating any other existing DEC codes. If the validation code is displayed at 15% torque, plus or minus 3%, it is possible the EDECU does not have the DAS plug installed and the 701 Delta engine will operate with 701 Charlie limiting values. Additional codes are listed in the Chapter 2 of the Aircraft Operator's Manual. On engines with EDECU and a DAS plug installed, the dual engine 10-minute limiting values will automatically switch to the higher single engine 2.5-minute limiting values when any of the following conditions occur. NP drops below 96%. Greater than 3% droop between reference NP and actual NP. Greater than 5% per second NP droop rate exists and NP less than or equal to NP reference speed. Should the crew fail to recognize the configuration via the torque meter on the MFD verification, you can easily achieve that by using FMS status page as associated in the note. Select the FFK status key, select SK4, soft key 4, air vehicle key, select soft key 3, DEC1, or soft key 8, DEC2 as applicable. Verify no-go status and applicable DEC message on NP demand channel or NVM fault, non-volatile memory fault. NP demand channel should show a DEC code of 25% plus or minus 3% showing a DAS plug is installed. NVM fault should show a DEC code of 15% plus or minus 3%, which means that no DAS plug is installed. The EDECU has a 5th cannon plug for the DAS and can be identified on pre-flight. In a contingency situation, an aircraft with an EDECU on one engine and a DECU on the other engine may experience torque splits due to the difference in contingency logic of the controllers. The engine with the EDECU will display higher torque while the engine with the DECU will try to match the torque up to the load sharing torque limit in order to provide and raise NP 3% above the reference NP. Engine alternator. The engine alternator supplies AC power to the ignition exciter and DEC EDCU. The engine alternator also supplies the NG signal to the cockpit. All essential engine electrical functions are powered by the alternator. If the alternator power supply to the DEC or EDCU is interrupted, 400 Hz, 120 volt alternating current helicopter power is utilized to prevent engine high side failure. Overspeed protection is still available. If the engine alternator should fail and interrupt the NG signal, a loss of the associated cockpit NG indication and activation of the engine out warning and audio will occur. Illumination of the master caution light will also occur. Overspeed drain valve, ODV. The functions of the ODV are: the ODV sends fuel through the main fuel manifold to the 12 main injectors. There are no start fuel manifold or primer nozzles on the 701 Charlie and Delta configuration. The ODV purges fuel from the main fuel manifold on shutdown to prevent coking. The ODV provides NP overspeed protection and hot start prevention. This is accomplished by cycling all fuel back to the HMU inlet and shutting off fuel flow to the engine. Hydromechanical unit. Control of the fuel to the combustion system is provided by the HMU. The HMU, mounted on the rear center of the accessory gearbox, contains a high-pressure pump that delivers fuel to the ODV. Various parameters are sensed by the HMU and influence fuel flow: variable geometry position, and engine anti-ice start bleed valve operation. There are two mechanical inputs from the cockpit to the HMU. The load demand system, or LDS, provides mechanical input directly from the collective output of the flight control mixer to the engine HMU to reduce transient engine and NR droop. The system acts as a load anticipator and then immediately inputs a load change to the HMU, which resets NG as required to maintain a nearly constant NP. This system makes gross corrections, which are fine-tuned by load sharing and provide power turbine governing functions of the DEC. If the engine power control lever is moved to lockout, then to an intermediate position, the engine will still vary power in response to collective signals. Collective movement is transmitted directly to the MMU. A bell crank on the mixer provides input to the push-pull load demand spindle, LDS, load demand spindle cables, and then to the engine HMUs via a rotary actuator. The rotary actuator is spring-loaded to increase collective direction to minimize system free play and will also drive the LDS to maximum demand, corresponding to full up collective. In case of a separation in the system resulting in full engine power available, at the mixer end of the cable, a shear pin and roll pin shear/roll pin is provided to prevent a flight control jam in the event of a load demand system malfunction. If the pin shears, the LDS cable to the HMU for the engine will drive full aft and produce maximum LDS demand. This may, under certain flight conditions, produce a torque split. If the pin shears and the load requirement of the engine is reduced, e.g. in auto rotation, the DEC will not have enough downtrimming authority to reduce torque to zero. Under this condition, the excess engine torque produced may be sufficient to drive the engine or NR to NP1 or NP2 overspeed. The engine power control lever operates the power available spindle, also known as the PAS, in the HMU. When the engine is operating in fly, the LDS and DEC control have maximum power available to be utilized. If the engine power control lever is placed in lockout, the NP1 or NP2 servo, normally controlled by the DEC, is locked out to its maximum power. Engine power must now be set manually by adjusting engine power control levers. The engine will still increase and decrease power in response to LDS, collective changes, DEC, and EDCU functions which utilize the NP1 or NP2 servo. TGT limiting, NP1 or NP2 governing, and load sharing are inoperative in lockout. Warning: going to DEC lockout to obtain additional power does not remove maximum fuel flow or NG limits. NR still may decrease below normal operating range if maximum fuel flow or NG limits are reached. Notes concerning engine indications. The change in engine oil temperature lower of -20 degrees Celsius is not an actual temperature or functional limit change. It is based on the physical reporting limits of the Engine Instrument Caution Advisory System, ECAS. The indication is not reportable below -20 degrees Celsius. The UH60M DEC and EDCU bias has been changed to -112 degrees Celsius. This provides for similar displayed limit indication numbers when compared to the UH60 Lima. The UH60 Lima was biased to show lower than actual indicating numbers on the central display unit due to the display's inability to show 4-digit numbers. On the UH60 mic, TGT display is an indication of 903 degrees Celsius. In reality is actually 1015 degrees Celsius for actual temperature.